We'll discuss today the test of goodness of fit. It is an important topic in the syllabus. So our aim will be to test whether the fitted line is well fitted. When we fit the straight line, whether it is fitted best or not. So this is the goodness of fit. So we'll have to test it. So there are three groups, like a theoretical priori, then statistical and econometrical criteria. So in theoretical priori, generally, we examine the sign and size of parameters. So when we fit the line, straight line, y is the function of x, and line is y is equal to beta naught or alpha plus beta x. So those alpha and beta, the parameters. What is the sign of the parameter? What is a plus sign or minus sign? Suppose a particular relationship between y and x, they should have inverse relationship. So definitely the regression coefficient beta should show a negative sign. Negative sign. That means if x is increased, so y will decrease. If this kind of relationship, then it will be reflected in the sign of the parameter. Okay. And vice versa, that means if they are positively correlated, suppose x is increasing, we are increasing x, and y is also increasing, then it will be reflected in the sign of the parameter beta. Then sign and size, it should not be abruptly high. If it is not well fitted, then it may so happen that the size of the parameter is very high or very low, which cannot be interpreted. So this is generally seen in theoretical priori. Then in statistics, we generally examine the standard error. We will get it later on. Standard error. Then we test the parameters. So there are different tests: t-test, f-test, chi-square test, and so on. So, but we will have to see the standard error, which related with mean and standard deviation of the series. So we will come later on. And thirdly, the commonly used R-square values. So when we fit the function, then we have to show the R-square values. So generally it is the square of the correlation, and it can be adjusted also. Adjusted R-square. That suppose R-square is 0.85. That means 80% of the variation has been explained by the independent variable. So like that. So it should be higher. The value ranges between 0 and 1. It doesn't exceed 1. So nearness to 1 is generally the better acceptable values. So we accept that the function is fitted well when R-square value is high. Now, goodness of fit. So measures dispersion of regression line. Measure is R-square. So best fitted line is estimated y is equal to beta naught intercept plus estimated beta 1 x. So error is EI is equal to YI minus estimated Y. So that is generally the unexplained variable, variation. And total variation is Y is equal to summation YI square is equal to sum YI minus Y bar square. So this means every observed value of Y minus, that is the mean deviation, minus mean of Y, square it. Just sum Yi minus Y bar is 0 because sum of deviation from mean is 0. But when you square it, positive becomes positive and negative becomes positive when you square it. So that mean deviated square term is summation Yi square. So this is explained variation. Okay. And summation EI square is equal to YI. So this is Y bar, that means mean. But when we subtract estimated Y from YI, so this square, this gives the unexplained variation. Okay, this gives the unexplained variation. So when we remember in our topic, linear algebra topic, that when we fitted a least square line, so two kinds of lines. One line passes through the average of Y and average of X. Okay, then the error is if the observed value is above the line, and so distance from that value to the average line, that is 1. That is the plus. And one is if the observed value is below the line, so the distance from this to the average line, that is minus, negative. This is smaller decimals. So for each value, each observation, we will find that if we sum up, then it gives the error. One for average value and one for observed. Then when is a least square line, not the average line, but the least square line, by following the two simultaneous equations for minimization, and then we will find, we will get Y estimated, and when we subtract it from each observation, so that becomes the error. Now this is unexplained variation, and to summarize, EI is equal to YI minus Y estimated. So that is deviation of the observations YI from the regression line. So this is from the regression line. Then YI is equal to capital YI minus Y bar, deviation YI from mean. And estimated YI is equal to YI minus Y bar. So deviation of the regression value, estimated Y from mean. Okay. So from these relationships, we can find out Y, we can find out Y bar. Okay. So from two, what is YI? If small YI is equal to this, then what is YI? Small YI plus Y bar. And from 3, Y estimated is equal to small YI estimated plus Y bar. Now, if we substitute the values of yi and yi estimated in 1, then ei is equal to yi plus y bar minus y I estimated plus y bar. So if we simplify, so simply we'll put the values here and we'll simplify. So if we simplify, then yi minus yi estimated. Then yi is equal to yi estimated plus ei. And because ei is equal to this, so this. The sum yi square, if we square it, is equal to sum yi plus ei square. This is equal to yi square plus ei square. Okay. Now, just a hint, yi is equal to yi estimated minus y bar. Then yi estimated is equal to beta naught intercept estimated intercept plus beta 1 estimated xi, and y bar is equal to beta naught estimated plus beta 1 estimated x bar. So it is the average line. So yi now come to this yi. This is, so yi is equal to beta 1 head xi into xi. So what is xi? Capital Xi minus x bar. Okay. Again, ei error is equal to yi minus yi estimated is equal to yi, and for this we will substitute minus beta 1 head xi. So summation yi is equal to beta 1 head summation xi yi minus beta 1 head xi square. Okay. But beta 1 estimated, we know that summation xi yi divided by summation xi square. So we have got it in two normal equations. Then yi estimate, sum of yi estimated ei, if we put the values, is equal to beta 1 into summation xi yi minus, again beta 1 means summation xi yi by summation xi square into the sum xi square. So this is nothing but, so if we cancel it, so it will be 0. So summation yi square is equal to summation yi square plus summation ei square. So there is a correction, just it was dropped. It is summation yi minus y square. So total variation is equal to explained variation plus unexplained variation. Summation yi square is total variation, and summation yi estimated square is explained variation, and summation ei square is unexplained variation. So explained variation plus unexplained variation is equal to total variation. Now let us explain variation as percentage of total variation. So what is the percentage of explained variation of total variation? This is summation y estimated square by summation y square. Okay, this divided by this, and substitute estimated y is equal to beta 1 x. So we have got earlier. Then summation y square, estimated y square by summation y square is equal to summation beta 1 estimated beta 1 x square by summation y square. If you break it up, it is estimated beta 1 square into summation x square by summation y square. Okay. Now, value of beta 1 is equal to summation x square by summation x square we have got earlier. So when we estimated through two normal equations, least square equations, least square method. So beta 1 was this. So square of this is summation xy whole square by summation x square. Okay. Then we get now summation y square by summation x square just by putting these values. Summation xy square by summation x square whole square. That means beta 1 square into this summation x square by summation y square. So by cancellation, after cancellation, we will get summation xy square by summation x square into summation y square. Now correlation coefficient, R correlation coefficient R is equal to summation xi yi by under root of summation xi square into under root of summation yi square. So if we square it, it will be summation xy square by summation xi square into summation yi square, or R square or capital R square. Generally we write as capital R square. So this is the coefficient of multiple determination. Okay. So R square explains the proportion of variation of y explained by the variation in x. So when x will vary, so what will be the variation in y in proportion? So the value of R generally it ranges between 0 and 1. There is a small correction that R square. So the value of R square ranges between 0 and 1. So it never exceeds 1. So higher is the value, better is the goodness of pitch. So why R square is a measure of goodness of pit? The higher is the value of R square, better is the goodness of pit. So it should be always nearness to 1. If the value is very low, then the line is not well fitted. So further, R square is equal to 1 minus summation ei square by summation y square. So we can split up, and summation yi square is equal to summation y estimated square plus summation ei square. From this, divide through by yi square and simplify, then you will get this. r square is equal to 1 minus summation ei square by summation yi square. So once we know the value of sum of the errors, okay, and sum of y square, okay, so if we know the value of this and this, yi square and ei square, we can find out the value of r square, 1 minus the ratio of this. Okay. Now there is another concept. This is the adjusted r square. So sometimes we use this adjusted r square. So r square should be adjusted. Say 1 minus, the formula is 1 minus, within bracket 1 minus r square into n minus 1 by n minus k, or adjusted r square is equal to, we can further break it, summation ei square by n minus k divided by summation y square by n minus 1. So the value of r square will depend on the number of samples, number of observations, how many observations we have taken, a sample we have taken, and number of regressors in the independent variable, number of independent variable. So generally in multiple regression, when there will be number of independent variable, y is the function of x1, x2, so on up to xn, and in that case, the number of observations and number of regression, the independent variable, will depend the value of r square. So when we can judge here, when suppose number of observation is very low and very high, then what will be the ratio? So similarly, number of independent variable is higher or lower, then what will be the ratios? So generally we found that if the number of observation is higher, then r square values will also improve. That means the goodness of fit will be better. So with this we have concluded the goodness of fit, and further we will discuss in other chapters. So thank you very much for watching, and keep on watching, and please subscribe and share. So thank you.